In this next little lecture, I'll talk about continental lithosphere and a little bit about platinum group elements, or PGEs. I'll start talking about some of the major differences between these different types of lithosphere. First between oceanic and continental lithosphere, but it actually turns out that the bigger differences are between cratonic and non-cratonic lithosphere. Talk a bit about the physical differences, differences in age, and geochemical differences. Next, I'll do a little side note on platinum group elements and how we can use them as indicators of mantle depletion, and just try and introduce the concept of element sensitivity and why some elements are more sensitive to certain processes than others. Next, I'll go through some models for forming continental lithosphere, including melting in plumes, subduction zones, and by stacking oceanic lithosphere. I won't go into which model is best at that point, but we'll deal with it a bit using a case study of Zealandia as an example of recent continental formation. All right, I hate to start another lecture with definition problems, but this is another one that's a little bit up in the air, and you'll see different versions. So in terms of what a craton is, there's kind of two main groups of definitions. The first one defines it based on the ages of the crust. So here's one from DeWitt and Hart in 1998. Archean cratons consist predominantly of granite greenstone sequences formed in the Archean. Pretty straightforward. The slight problem with this one is that some very large areas of non-Archean crust are described as cratons. So the Siberian craton is, I think, largely Proterozoic, and the Amazonian craton is similar. An alternative definition is based around the idea that it's of stability, that these are areas that have been stable for a long time. So this one's from Bleecker, 2003. Craton, a segment of continental crust that has attained and maintained long-term stability, with tectonic reworking being confined to its margins. So the problem with this one is that there are some things that are called a craton that are definitely not stable. So the North China craton appears to have rifted and lost a bunch of its lithospheric mantle at some point in the past couple of hundred million years, something like that. And then just a question of is thick lithospheric mantle a requirement for stability? Is this part of the definition or not? There's a bunch of variations on it. I'm going to try and largely avoid it, but we're mainly going to be talking about cratonic mantle. And so just taking this definition out of Hawksworth et al. 2017. Continental lithospheric mantle beneath Archean age crust tends to be composed of dehydrated, highly depleted mantle peridotite, resulting in it being intrinsically buoyant and strong. Some lithospheric mantle beneath Proterozoic crust may have some of these characteristics as well. Okay, so what are the major differences between oceanic and continental lithosphere, and between cratonic and non-cratonic continental lithosphere? Just starting with the physical differences, here I think the main differences can be seen between oceanic and continental. So in terms of minimum thicknesses, oceanic lithosphere, in terms of thermal lithosphere, is essentially just the same thickness as the crust at a mid-ocean ridge, because you have a asthenosphere upwelling right up to just beneath the crust. So that could be, about 0 kilometers at these ultra-slow spreading ridges. It could be something like 8 at a more typical mid-ocean ridge. On the continents, it's a little bit of a semantics problem, because if you continue to rift continental crust, you'll eventually open up an ocean basin. But beneath a lot of continental rift zones, it might be as thin as 40 kilometers or so. So very, very thin lithosphere. In terms of maximum thicknesses, in old, cold oceanic lithosphere, it'll get up to about 100 to 100 or 125 kilometers thick. Continental lithosphere can get a lot thicker, maybe around 200, 220 kilometers beneath the cratons. And according to some recent geophysical work, it might get very, very thick beneath continental collisional belts, such as the Himalayas, or beneath Iran, where it can be close to 280 kilometers thick. In terms of density, all these densities are reported at a temperature of 800 degrees C and depth of 90 kilometers to cancel out thermal expansion and increases with pressure. So oceanic lithosphere might be in the region of 3,360 kilograms per meter cubed. Continental lithosphere shows a much bigger variation, and it ranges from very, very light, 3,320 kilograms per meter cubed in Archean cratons, up to something a lot more similar to oceanic lithosphere in under younger continents. On the right, I've just shown again the same map of lithospheric thickness for North America from Priestley and Mackenzie 2006. Okay, so just as a general rule of thumb, Archean lithosphere tends to be the thickest, followed by Proterozoic, followed by Phanerozoic continental lithosphere, with Oceanic lithosphere being the thinnest. There are obvious exceptions, so continental rifts tend to have quite thin lithosphere, and reworked cratons. This is like the situation I mentioned before with the North China craton, which actually has relatively thin lithosphere, maybe 100 kilometers or so thick, despite being Archean crust at the surface. On the right here is just a big compilation of pressure and temperature data from kimberlite xenoliths from Carlson et al. 2005. And you can see that by plotting up all these pressures and temperatures, you define a geotherm. This is the relationship between pressure and temperature. And because continents have thick lithosphere, and this is it's removed from convection, it's not convecting with the asthenosphere, then there's a conductive geotherm through the lithosphere. And because a conductive geotherm, aside from a little bit of radioactive heat production, is essentially just a straight line between 0 and the mantle adiabat, then it ends up being colder at a given depth than convecting mantle. And the mantle adiabat is more or less the same temperature the whole way up, although it varies a little bit because of the changes in pressure. In terms of age, this is a pretty obvious and striking difference. Oceanic lithosphere is mostly less than 200 million years old. It gets pretty old at the margins of the big oceans, and possibly in the Mediterranean, we might have some relict bits of the Tethys Ocean lithosphere that could be 280 million years old or so. But in general, it's pretty young. Continental lithosphere can be a lot older. And on the right here is just a compilation of rhenium depletion ages for various peridotites. On craton, brought up by kimberlites. Off craton or craton margins, also brought up by kimberlites. And finally, off craton, alkali basalt hosted peridotites. And you can see that in general, the cratonic peridotites are a lot older. And the oldest ones can range up to 3.5 billion years old or so. Hopefully some of you will think back to the previous lecture and think, well, if we are incorporating these chunks of old mantle into younger lithosphere, could some of this continental lithosphere actually be a lot younger than it looks and just have these chunks kind of convected into it? It is definitely possible. We have some pretty robust data that shows that at least some of the continental lithosphere is very old. So on the left here is just a plot of, it's a rhenium-osmium isochron using diamond inclusions, I think sulfides, from the Slave Craton up in Canada. And you can see that it more or less lies on a 3.5 billion-year-old isochron. So the fact that we have these ages shows that there was, these diamonds are very, very old. And then from the thermobarimetry of inclusions, we can also see that the lithosphere was already quite thick and deep at that point. And the compositions of some of the inclusions are very depleted. So on the right is just a plot of olivine magnesium number from Lutzolytic and Hartsbergitic inclusions in diamond. So at least some of the continental lithosphere is old, and at least some of it was thick and deep back in the Archean. Okay. In terms of geochemistry, off craton, a lot of the rocks actually look quite similar to oceanic lithospheric peridotites. So in the top right, I've just plotted I've shown a depletion trend from Boyd 1989, and this is a plot of olivine magnesium number against modal olivine percentages. So as you melt, you're preferentially removing iron, calcium, aluminium, and silicon relative to magnesium. So this is essentially dissolving the aluminous phase, spinel or garnet, clinopyroxene, and orthopyroxene, and the residue that you get left is increasingly pure olivine and increasingly magnesium-rich olivine. So fertile peridotites start with relatively low modal olivine percentages down in the bottom right, and as you melt, you get more and more olivine, more and more Mg-rich, and that produces that trend marked by the black arrows. That's the oceanic trend here. The most depleted compositions you get from ophiolites, which are related to subduction zones. And from the same paper, just below that, there's a plot of off-craton xenolith compositions, and you can see that they're pretty much following the oceanic trend. We're not getting anything crazy depleted. The highest Mg numbers are about 92, and the highest modal olivine percents are about 90. The plot on the left there is just to show you this increase in olivine percentage as you melt, and at a pressure of about 2 gigapascals or 60 kilometers or so, you basically end up with a pure olivine residue after about 40–45% melting. Cratonic mantle is more depleted than oceanic lithospheric mantle or off-craton continental lithospheric mantle. So a couple of ways of measuring this: it tends to have higher olivine Mg numbers, tends to have lower aluminium and calcium contents. And so because we're removing some of these elements like iron as we continue to deplete it, and we're leaving just more and more Mg-rich olivine, then it's lower density. So the density that we talked about in the previous slides is just reflecting the composition here. So because it's lower density, that might make it more stable. It's essentially floats, it's buoyant, compared to younger lithospheric mantle. So in the top right here, you can see a plot from Griffin et al. 2009. It's just calcium against aluminium. This is a little bit, I think it's either using average data or it's a little bit schematic. So you can see that in general, the Archean stuff is going to be lower in calcium, lower in aluminium, and as you get younger, the composition starts to resemble a stenospheric mantle more and more. However, there's a lot of scatter in these compositions. It's not as neat as it looks in that plot. And the figure in the bottom right is from the same paper, just the aluminium percent against the average Mg number of the olivines. And you can see the dashed line marks lithosphere that is below crust that's less than 1 billion years old, and the samples labeled Prot, a Proterozoic 1 to 2.5 billion years old, and then the other Archon and Capval are mantle samples from beneath Archean crust. And you can see there's actually a lot of scatter, and even though the Archean ones tend to be more depleted, then they do actually overlap some of these younger prototypes as well. In the bottom is just re-emphasizing what I mentioned before about the density. And you can see that by the time you've had 25 or 30% melting, you start to get a density comparable to Archean lithosphere with about 3,320 kilograms per meter cubed, or 3.32 grams per centimeter cubed. All right. So the main points is that continental lithosphere is generally a lot thicker and older than oceanic lithosphere. However, the young stuff is pretty geochemically similar to oceanic lithosphere. The largest compositional differences are seen between highly depleted cratonic ancient lithosphere and young continental or oceanic lithosphere. Okay, just have a little sidetrack into using platinum group elements or PGEs as indicators of mantle depletion. So I just want to get you thinking about what elements are sensitive to different processes. So traditional lithophile trace elements are pretty useful when we're looking at melts. They're sensitive to degree of melting, differences in source depletion. And I've just tried to illustrate this with a really, really basic fractional melting model using thorium, which has a bulk partition coefficient of something like 1 times 10 to the minus 4. It's super incompatible. So in the top plot is the thorium concentration in the melt for an instantaneous melt, so that's each little increment, or the aggregate melt, which is where you pool these all together and average it. And you can see, and it's plotted against degree of melting. So you can see that if you're looking at a basalt, this might be quite useful. For example, if you want to see if a basalt's formed by 1% melting, that might correspond to a thorium concentration of like 10 ppm or so. Or if it's formed by 10% melting, it might have a thorium concentration of 1 ppm. Okay, so we can clearly use that to look at the degree of melting and source depletion and so on. But it's not very useful when we're looking at residues. So below is a plot of what happens to thorium concentrations in the mantle residue with degree of melting. Now you can see that even by a very, very tiny amount of melting, less than 0.1%, basically all the thorium is gone from the residue. It's all gone into the melts. And what we're seeing in the basalts is just increasing dilution of that thorium by adding melts that don't have any thorium in them. But for the mantle samples, we just see nothing. So the thorium gets rapidly depleted in the early stage of melting, and it's really not going to give us any sort of a hint whether these mantle samples experience a little bit of depletion, like 5 or 10%, or a lot of depletion, like 30%. The other problem is that small degrees of metasomatism, particularly by low degree melts, and so this is re-enrichment when a melt passes through, completely swamp the incompatible element concentration. So it's just not useful for mantle samples. So this is why we're going to talk about PGEs. The platinum group elements are ruthenium, rhodium, palladium, osmium, iridium, and platinum. I've just highlighted them in the red square there on this periodic table. They're highly siderophile, which means that they like to be in metals or alloys, and they're also chalcophile, which means that they like to be in sulfides. They often get grouped with other highly siderophile elements, so rhenium, which we obviously talked about for the rhenium-osmium system. It's very useful to group it in with the PGs, and gold, because we're interested in mining and making money and so on. The chalcophile behavior of the PGEs means that you get a very different fractionation when you are melting, when there's sulfide present in the mantle source or when the sulfide has been exhausted. So typically sulfide should be exhausted by about 10 to 20% mantle melting. So because the PGEs have different behavior before and after this degree of melting, they're very sensitive to melting extents around this range. Okay. So on the right here is just a plot of what will happen to the PGE contents of a aggregate melt. So this is a pooled fractional melt with degree of melting. So before sulfide exhaustion, all the PGEs are very compatible in sulfide. So all the melts are very low in PGEs. So you can see that between 0 and 10%, the osmium, iridium, ruthenium, and platinum and palladium in the bottom plot are all very, very low. As soon as you exhaust sulfide, though, which in this model happens about 10% melting, the IPGs, which are iridium PGEs, osmium, iridium, and ruthenium, remain very compatible in the mantle residue. So that's because they're either compatible in silicates, so ruthenium might be kind of compatible in olivine, or they make alloys. So I've said nuggets here because these are really like nanoscale, tiny little alloy grains, but because there's not much PGEs in general, they end up controlling the whole rock budget of the PGEs. So osmiridium alloy would be an example of this. In general, platinum and palladium, which get referred to as the platinum PGEs, which is a bit dumb, and rhenium are very incompatible once sulfide is exhausted. I'm not really going to talk about rhodium because it varies depending on the conditions, and it's a bit weird. Okay, so on the whole, melts before sulfide gets exhausted are very low in PGEs, and melts that form after sulfide exhaustion have high PPGEs, platinum and palladium, but moderate or low IPGEs, osmium, iridium, ruthenium. Okay, so the flip side of this is we can use it in mantle residues as an indicator of depletion. So in these couple of plots from Olbach et al. 2015, different PGEs are plotted against aluminium, and this is an indicator of depletion. As you extract melt, you're extracting aluminium, so the lower aluminium samples are more depleted. In the top plot, you can see ruthenium. The stars are some sort of starting composition, depleted mantle or similar, and has about 4 weight % aluminium. And as you melt, your aluminium is dropping, so it's moving left along the plot. But the ruthenium is compatible, and it's not really going anywhere. So the ruthenium content in highly depleted samples with low aluminium is actually pretty similar to enriched samples with high aluminium. There are a few samples that get removed to low IPG contents. It's not, the process isn't completely understood. It might be something to do with oxidizing melts passing through, but we're not going to worry about that. By contrast, the PPGs, so plotted here is palladium on the bottom figure, they become strongly depleted. So again, starting at the red star, as you melt, removing aluminium, it moves to the left, and then at the point that sulfide is exhausted, and it happens at different points at the different pressures of the different dashed lines, the palladium content starts to drop quite quickly in the mantle residue. And so you can see that some of these mantle residues go down to very, very low palladium concentrations, much lower than we ever see in any of the samples for ruthenium. There is a fair bit of scatter because of metasomatism, so this is a secondary enrichment process where melts passing through dump a bit of palladium as they go. And this kind of metasomatism is very common in kimberlite-borne cratonic mantle xenoliths. But on the whole, we can see that the palladium gets a lot more depleted. PGEs often get plotted on these chondrite or primitive mantle normalized log patterns. So I hope this is pretty familiar from trace element patterns. But instead of ordering them in terms of compatibility, like you do with trace elements, they're actually ordered in order of pure metal melting temperatures. This is just some weird artifact of how people used to do it in the past. Luckily, it pretty much corresponds to compatibility. So in general, the more compatible IPGs are on the left of the plot, and the less compatible PPGs are on the right. So I just have a few of these log plots from different settings from Pearson et al. 2004. And you can see the Cratonic periodicites on the left. There's 3 different groups based on the amount of rhenium enrichment they have. So these were probably all at some point depleted in rhenium, but then metasomatism added rhenium back in. But in general, you can see that the platinum and palladium is quite depleted, and the platinum here, and here, and here, and palladium, the next one along, is actually a lot lower than the osmium, iridium, and ruthenium. So this is consistent with what we were saying. The PPGs are incompatible after 10 to 20% melting, and they get extracted and into the melt, and the residue is left depleted in PPGs. However, for all of them, the IPGs are pretty high and they're flat. They're not really going anywhere. In terms of non-cratonic samples, so on the right there is some PGE plots from some circumcratonic prototypes from Namibia, some prototypes from the Baikal Rift Zone, which is Proterozoic lithosphere, and some recent orogenic prototypes from Morocco, I think, Beni Brissaire. And you can see in all of these, the IPG contents remain high, but also the PPG contents are high. So they're not getting depleted. So we're not having such an extensive degree of mantle depletion here. So this is consistent with what we said based on the Mg numbers and the aluminium, that you get a high degree of melt extraction for cratonic prototypes. All right, so the main points of that section is that because PG is a chalcophile, they're sensitive to high degree melting processes. After sulfide exhaustion, which probably happens somewhere around 10 to 20% melt extraction, osmium, iridium, and ruthenium are compatible, whereas platinum, palladium, and rhenium are incompatible. Cratonic mantle lithosphere is more depleted in platinum and palladium than recent mantle lithosphere, which is consistent with the high degrees of melt extraction. We'll just talk about some different models of continental lithosphere formation. As I said, I'm not going to get into which one's my favorite or which one's best. We'll deal with that later. Okay, so the big thing to note is that continental lithosphere is a lot more complicated than oceanic lithosphere for a number of reasons. The first one is that it's a lot more long-lived. So because it can be up to 3.5 billion years old, we have a lot more potential for metasomatism. We also have a lot more uncertainty about how much continental crust there was that long ago, how it was forming, different processes in the early Earth. Obviously, that complicates everything. There's also this issue of continental collisions being a lot more complex than oceanic subduction. So in the top diagram there is just a sort of a schematic diagram of the Himalayan collision. So on the left, you can see the Indian lithosphere is thought to be thrust under Tibet. So you have this possibility that actually the crust might be completely unrelated to the lithosphere beneath it if you have this crustal underthrusting. Another big question is, unlike oceanic lithosphere, where it's basically formed, trundles along, gets subducted, we don't actually know if continental lithosphere was thick when it formed or whether it got thickened by later collisions, because it can get squashed up. And as I mentioned before, in continental collisions, like in the Himalayas, the continental lithosphere might be up to 280 kilometers thick. So there's definitely potential to move things around relative to the crust above and thicken it after it forms. Just splitting the models into different types, you can broadly divide continental lithosphere formation into high and low pressure melting. High pressure melting is basically plume melting. So because of the elevated temperatures in the plume, you should start to melt at a greater depth. And potentially you can get a long column of depleted lithosphere that that would make nice, thick, potentially continental lithosphere. If you have low pressure melting, which is either a mid-ocean ridge or in a subduction zone, because the depths of melting there might only be as low as 60 to 100 kilometers, then to get some of these thicker continental lithospheric thicknesses, you actually need to squash it or thicken it or stack it in some way afterwards to make those greater thicknesses. In any of these cases, as I said before, the lithosphere and the crust above it, the formation of the crust and lithosphere could be related to one another, or the lithosphere could be underthrusted or accreted later, and they might be completely unrelated. If they are related, then any model that's going to explain the lithospheric mantle also has to account for how we generate continental crust. Okay, so high pressure plume melting models, these are pretty straightforward. You have plume upwelling, which causes mantle depletion over a large depth range. Some of the advantages of this model is that you can easily generate thick continental lithosphere without having to worry about thickening it later. There is some evidence that you can get thicker oceanic lithosphere beneath oceanic plateaus, so we have a potential to generate thick lithosphere like this, some evidence that might happen. It also produces highly depleted mantle. So on the right is just a schematic diagram of a plume forming beneath oceanic lithosphere, and you can see that as it upwells at the base, you're going to have the least depleted stuff, and then as it continues to upwell, greater degree of melting as it depressurizes, and you get the most depleted at the top. This is for a modern plume, so at the top we might get a mantle with an Mg number or 4-strike content of about 91.5. But if this was happening in the Archean or the early Earth, then potentially it's a lot hotter, get higher degrees of melting, we could make much more depleted residues. So the nice thing about this, getting the highly depleted mantle at the top and the less depleted mantle at the bottom, is that this meets the Isopycnic hypothesis, which I'll talk about in the next slide. The big drawback to this one is that we do see plumes on the modern Earth, but we don't really see any evidence of them forming continents. So is this something that happened in the ancient past, or are these, is plume lithosphere just generated and then it ends up being completely unrelated to the continental crust and thrust under later? There's also some evidence that on the modern Earth, where we do get plumes impinging beneath continental lithosphere, it actually erodes the continental lithosphere and makes it thinner rather than thickening it. So that's not very useful. And finally, where are all the plume melts? So if you imagine this big, thick column of mantle melting in a plume, if you're melting from a depth of, say, a couple of 100 kilometers up to near the surface, and you're melting it by even just 20%, then there should be about 40 kilometers worth of plume melts formed somewhere. So if we want to generate a lot of continental lithosphere with a plume, then we need to figure out where to put all these plume melts, or why we don't see them. Just a brief aside to talk about the isopycnicity hypothesis, and this is put forward by Jordan. In general, the density of mantle rocks increases with increasing pressure. It decreases with increasing temperature because of thermal expansion, and it also decreases with depletion. So if you imagine that you had thick continental lithosphere, but it was the same composition as the convecting mantle around it, this would actually be unstable. Because it's thicker, and because you have a thicker conductive layer, the temperature would be lower at a given depth, so it should be denser, and that should convect away. The other kind of like output of this is that if it's denser, then cratons should be low-lying because of isostasy, which I hope you guys are familiar with. Yeah? Okay, great. And what we actually see is that cratons are not particularly low-lying at all. They're generally just areas of low topography, but they're not basins or shallow areas. So Jordan came up with this isopycnic hypothesis to kind of explain this, and this is the idea that there's a balance between chemical and thermal density. So essentially, you offset this increased density from temperature by having more depleted mantle, which is chemically more buoyant. So if you have the most depleted residues at the shallowest or coldest levels and the less depleted stuff at the bottom, then this should stabilize your craton, and then you can preserve a craton for billions of years. On the right here is just a schematic diagram of what this looks like. So on the left, you can see the temperature increases with depth, And because it's increasing with depth, it's getting less dense. So that's the density anomaly is getting smaller. It's becoming more similar to convecting mantle. In terms of composition, then the Mg number is higher. It's most depleted at the top and it's least depleted at the bottom. And this will mean that you have the opposite density anomaly from composition. And so when you add those all together, the density, the thermal and chemical effects balance out, and you have a pretty constant density throughout the profile of the lithospheric mantle. There have been some recent questions as to whether continental lithosphere is actually isopycnic or just in some specific areas, or even whether if you have a continent that's isopycnic now, would it still be isopycnic in the ancient past, or does this change over time? But a lot of people do believe that this is a requirement for stable continental lithosphere, so I'm teaching you it, and yeah, make what you will of it. Okay. In terms of low pressure models, the first one I'll talk about is oceanic lithosphere stacking. I call it stacking here because you do need some way of thickening oceanic lithosphere to make it similar to what we actually see under continents. So the idea here is that oceanic lithosphere forms at a mid-ocean ridge, and then it's stacked in multiple subduction episodes, possibly with a little bit of extra melting as it gets pushed into this stacked configuration. So in the top right, you can see a diagram of mid-ocean ridge. This one's actually for an Archean ocean ridge, just to kind of illustrate that if mantle temperatures were hotter in the Archean, then potentially we'd have a thicker melting zone, so thicker depleted lithosphere, but also you'd then generate more magma, so you'd have a thicker oceanic crust on top as well. And below is just a cartoon of how this stacking might look. So in this case, basically, you are subducting oceanic lithosphere. At some point, for whatever reason, it gets jammed up, it gets stuck, and then the slab breaks off, and then you have another episode of subduction, and it jams up, slab breaks off, and you basically do this over and over again until you've made a nice broad craton. Then you need some sort of second remelting or another to generate the continental crust on top. So the pros of this one is that in Cratonic mantle in particular, we do see quite a lot of eclogite and pyroxenite. So in this model, this would be trapped chunks of oceanic crust that got stuck in the mantle during these subduction episodes. And a lot of authors now favor low pressure melting to explain the chemistry of lithospheric peridotites. The cons is that it's a little difficult to make continental crust like this. You need some sort of remelting of these thicker oceanic crusts to make something like a TTG, which maybe eventually starts to look like continental crust. It's also not intrinsically isopycnic, because if you look at these slices, in each of these different stacks, the most depleted stuff is going to be closest to the crust, and the least depleted stuff is going to be at the bottom of the oceanic slab. So you require some sort of later reorganization to meet this isopycnic idea. This also, to me, is a little odd, is that you need to constantly, or at least several times, start subducting, break off a slab, start subducting, break off a slab. And obviously that does become a bit of a problem back in the Archean, where people are still arguing about whether subduction was actually happening or not. The second low pressure option is subduction zone melting. So this one's pretty straightforward. You have a mantle wedge and a subduction zone, and as the oceanic lithosphere is subducting, this generates a corner flow in which mantle is dragged in under the island arc and then dragged down with the slab. Water coming off the slab causes it to melt. So the pros here is that it readily explains the mantle and crust formation. Obviously, this doesn't need to be an issue if the crust and underlying mantle aren't related, but it's kind of like a nice, easy way of doing things. Because arc magmas produce compositions that are pretty similar to continental crust. So average compositions in a continental arc are andesitic, which is more or less the same as the average composition of the continental crust. It's also the only process that can generate extremely depleted mantle in the present day. So if we're looking at some of these ancient depleted mantle samples, then this is one that we know for sure this works, and it does generate these really depleted peridotites. One of the cons is that because of the way the flux melting is happening here, and because of the way the corner flow operates, you actually get the most depleted mantle at the bottom of the mantle wedge, because of the way it's being dragged in and then down. So if we want to meet this isopycnicity hypothesis, then we need some reorganization and then some later thickening. And then obviously, same as the oceanic stacking one, is we have to ask whether subduction was actually active throughout Earth history and whether it can generate really ancient continental lithospheric mantle. Okay. So the main points are that the formation of continental lithospheric mantle is a lot more complicated than oceanic mantle. It's long-lived, it can be laterally accreted or thickened, and we don't understand continental crustal growth as well. Models for formation can be broadly divided into high-pressure plume melting and low-pressure models, which could either be a mid-ocean ridge or a subduction zone. And all of these have strengths and weaknesses. Okay, I'll just talk a little bit about Zealandia, which is the youngest continent, as a case study of how you might form continental lithosphere in the present day. So Zealandia, which you may or may not have heard of, is the 8th continent, supposedly. It's a largely submerged continent around New Zealand. So just in this diagram on the right-hand side, you can see continental lithosphere, or continental crust, sorry, is marked as yellow, whereas oceanic crust is marked in blue. So you can see it's actually largely submerged. The emerged crust of New Zealand is marked in grey. So the nice thing about this is like a kind of natural laboratory for how you might build continental lithosphere is that the oldest rocks here are only 500 million years old, the Cambrian age, and there's no isotopic evidence of all the crust. About 120 million years ago, this formed part of the arc margin of Gondwana, one of the chunks of Pangaea. And so you had subduction going on under Zealandia, which was attached to Australia and Antarctica. These are obviously rifted apart since then, and Zealandia is pretty much fully detached from Australia, and there's the Southern Ocean between it and Antarctica. So the crust is predominantly formed of arcs and metasedimentary terrains, and these were mainly accreted to this Gondwana margin during the Phanerozoic. During the Cretaceous, subduction stopped due to this, I don't know if you can see it in the kind of beige color there, the Hikudangi Plateau. That basically jammed up the subduction zone, or that's the interpretation, and subduction stopped. After that, it rifted from Antarctica and Australia, as I mentioned. And on this plot, on this diagram, the green stars are where Scott et al. Had mantle samples available. So these are a mix of ophiolites. The prominent green line there is the Dun Mountain ophiolite, which gave the name to Dunite. And the green stars are alkali basalt xenoliths mainly. Okay. In terms of composition and structure, it's generally quite thin lithosphere here. It does get up to about 160 kilometers thick beneath the Southern Alps, and these are the Southern Alps of New Zealand, not the ones in Italy. There's a mix of moderately depleted and highly depleted prototypes. So a couple of ways of looking at this. The average olivine Mg number from these different samples ranges quite strongly from about 89, which is basically the same as fertile mantle, as convecting asthenosphere, and it goes all the way up to 92.5, which is extremely depleted. On the right is a plot of aluminium box and whisker plots for these different localities. The coloured ones are from New Zealand, and the ones on the right are comparisons to global abyssal prototypes, rock prototypes, and some depleted prototypes, and then the light grey ones are various Archean cratons. So you can see that some of these samples go down to extremely low aluminium contents, so below 0.5%. And this can't be, you can't get this low aluminium by high pressure melting on the modern Earth. And that's because at high pressures, garnet is stable to extremely high degrees of melting, about 50% or so. So you can see the red bars going across are for 30% melt extraction at 5 GPa, 3 GPa, or 2 GPa, which is about 150, 90, and 60 kilometers depth. So there's evidence that at least some of these require low pressure melting. There's also no systematic relationship between how depleted the mantle is and the position relative to the Cretaceous arcs. Looking at the lithosphere ages, and then just doing another TRD curve diagram again from, this is another compilation from Scott et al. You can see that some of the TRD ages range up to 2.7 billion years old. And I hope this feels a little bit familiar from what we were talking about with ophiolites and abyssal prototypes. The TRD ages also have a pretty similar distribution to abyssal prototypes. You can see this kind of broad peak that's centered at around 1.2 billion years old, going back to about 2 billion or so. It's very similar to the global compilation of abyssal prototype data. has a bit of a stronger peak at around 500 million years old, and we might expect this from the fact that this is when the crust started to form in Zealandia. There's absolutely no relationship between these TRD ages and various indicators of depletion. So on the bottom right plot here, you can see just the 187 over 188 osmium ratios, which of course sort of equivalent to the TRD ages. The oldest TRD ages are the lowest 187 at the bottom, and the metasomatized are the ones at the top where you have high 187 and they have higher 187 over 188 osmium relative to convecting mantle. And these are plotted against palladium over iridium. This is using a PPGE, so an incompatible platinum group element, divided by an IPG, or a compatible one. So as you deplete it, because you remove palladium preferably in preference to iridium, then it moves towards the left on that plot. So if all the lithospheric mantle here was ancient, let's say it formed in the Archean or something, and then was variably refertilized, then we'd expect some sort of correlation, because as we refertilize it, we'd be adding aluminium, we'd be adding palladium, we'd be potentially changing the olivine Mg numbers, and adding rhenium, so we should mess up the TRD ages. But there's no relationship whatsoever. So this actually kind of implies that we have a similar situation to the Oceanic lithosphere I was talking about before, where you're bringing in these chunks and they're just of previously depleted mantle, and they're just getting amalgamated into the lithosphere. So Scott Stahl put this together for a model of how the continental lithosphere formed in Zealandia. And so it basically starts with these variably depleted mantle chunks in the convecting mantle that are swept into subduction zones beneath Zealandia. In some cases, there might have been additional flux melting from the subduction zone, fluids being driven off, and this could help explain why there's just absolutely no correlation between these levels of depletion and the ages. So what's happening here is a combination of lateral accretion of previously depleted mantle and low pressure melting in a subduction zone. And this low pressure melting probably gives us the really, really low aluminium peridocites, the really depleted stuff. And then actually, because subduction is not ongoing in New Zealand, it's kind of like there's a subduction zone to the north and the south of it, but it's got a big strike slip, so it's fault through the middle. But you can see that the lithosphere has actually begun to thicken beneath the mountains there, potentially a bit of compression. So this is a story of low pressure melting and then compression. There is a little bit of a plume involvement here, and that Hikurangi plateau that I mentioned is it's an oceanic plateau. It's thought to have been generated by a plume. And so some of the lithosphere underlying Chatham Island, which is right out in the east of Zealandia, might actually be plume derived. So the main points here is that the Zealandia continental lithospheric mantle is variably depleted with some extremely low aluminium peridotites that must have formed by low pressure melting. TRD ages do not correlate with the degrees of depletion, and some ancient Archean ages are recorded. The best explanation for this is accretion of ancient mantle chunks, similar to what we see in abyssal peridotites and ophiolites that were variably remelted in Zealandia's subduction zones.